Hello, everybody. Today we will start the long-term course on the embedded systems. That means we will have about 15 meetings, 15 session on this course. So, and finally, we will have an idea about what an embedded system is. So let's start with the presentation. Okay, just a second. Okay, so embedded system. In this session, we will have a small introduction or a quick introduction to the embedded system, what an embedded system is, and we will discuss about some architectural consideration regarding the embedded system. First of all, I will start with presenting myself. I'm university lecturer and Technical University of Moldova, starting from 2003 till present. So I managed to teach courses like programming in electronics, microprocessor and interfaces, embedded system in different various combination in English and Romanian and even Russian. Internet of Things for PBL. So as you know, we'll have a parallel course on the Internet of Things. So I'll make some relation between these two courses, and most probably I will give you even a path how to define and how to develop things in the Internet of Things. Okay, and same course on the Internet of Things I have for another series on the fourth year. Hardware descripting language, electronic programmable system. That means here we are defining some hardware using hardware description languages. Some project management and project development tasks, course for developing those skills. Embedded system for master and digital design and verification. Okay, my experience comes from industry, of course, because everything you will see in this presentation is confirmed from my experience. I started to go to the industry from about 2005 when I started with digital design. Even I can say that I learned the embedded system and C programming language first from the digital design. That means I did not enter it into the programming through the software engineering. I came here through the hardware engineering, and so I understand every line of code, how it's processing on the central processing unit, so we can discuss about that and about the optimization. Also, a period I was working for another company, Silicon Service in Romania, regarding digital design and verification, some EDA tool, electronic design automation tool, for PCB and for integrated circuit layout advising or on the design rule checks. And my most valuable for experience for these cars was working for automotive industry, for the hybrid electrical vehicle department, and for autonomous driving assistance system department. So I have a lot of experience. More than it, I was working for safety monitoring function section. That means that I know how to write some the right approach to how to prevent humans from device injury. Okay, more than it, in parallel with my growth as an engineer, I started also in 2003, and in 2011 we initiated the engineering club Microlab. Most probably most of you already heard about that, and here we grow together. That means anyone who wants to learn more and to have more than they can learn on the university, they can come here and develop extracurricular some projects and participate on different community event, and participate on some extracurricular programs like, let's say, autonomous driving bootcamp, robot factory bootcamp, PCB design bootcamp, Internet of Things bootcamp. By the way, this year we will launch another a new program regarding digital design and verification, and we will write some code, and it will convert directly to some hardware. That means we will learn how to develop a central processor unit, okay, or a memory, how to build by writing some code. Okay, so also you can involve in some competition. You can have your diploma project here if you are interested in this domain, and of course involve in projects that are currently here. My student background is I come from Cochin. I have my license or bachelor degree in microelectronics. I have 2 masters actually, one in here in Moldova and another in power converter and biomedical engineering in Iași, because I wanted to see how is the education in another side and what I can bring from there. And always in my experience or as a lecturer was always to bring something new, because let's say the things that was before I started to be a professor or a lecturer in university, things was an old style school, and let's say I tried to change something by myself. Okay, I started PhD in microelectronics and nanoelectronics, but I switched recently to embedded system, and now my direction is spread out electronics, or say, let's say system electronics distributed, spread out electronics with autonomous evolution of the configuration. But let's say maybe parts of my project are included in these cards, and you will not find some references except in these cards. So please take care, because maybe you will have situation when okay, I didn't hear, I can't find such information another side. Okay, let's see what is an embedded system. According to the Wikipedia, okay, by the way, Wikipedia is not an official source of information, but by the way, okay. But it's about what the people think about some things. Okay, so according to the Wikipedia, an embedded system is a computer system or a combination of computer processor, computer memory, input, output, and peripheral devices. By the way, you see that is a perfect description of a PC, or okay, that has a dedicated function within a larger mechanical or electrical system. From another side, it is embedded. This computer is embedded in a as a part of a complete device, often including electrical or electronic hardware or mechanical parts. And I have here two examples. Let's say we see here an image of industrial computer. That means the computer that we know it's not necessary to look like our laptop or a desktop PC. Even this box can be a computer, and we see this even, it seems that it has a more a new processor, but the interfaces are still an old style. Even most probably this is okay, it's a COM port. So it's used for industrial purposes. Okay, more than it, and this image on the right, we can see how it's looking. When we are thinking about an embedded system, we should have imagined that it has a mechanical shape. Okay, it has some electronic circuits, and it has some microcontrollers. So from in these cars, an embedded system is a device that is made on mechanical engineering, electrical engineering, and software engineering that are working together to have a result. But from the point of view of structural point of view, it's a device or a device where was embedded an processor or a processing unit. Okay, then let's see the next. Now we see a lot of application of embedded system. Even in the home, we can see a lot of smart home appliances like kettle, let's say, temperature or air conditioning. Now is very popular some intelligent light system, and what is interesting that you can buy on any market some intelligent system for the home, and you can use it the most advanced. Even you can connect to the internet or your tablet, and you can manage it remotely. So it's a kind of is a step or a part of the nowadays hype regarding the Internet of Things. So now just a short introduction what an Internet of Things is. Internet of Things or Internet of Everything defines a network of objects that incorporate or embed some electronic circuits and allow communication through the existing infrastructure. Means the most common infrastructure is the internet. Okay, that means that every object in the world can be connected to the worldwide network. So for the purpose of remote control or monitoring. So we have here, let's say, the various things that can be connected to the internet and some pictures regarding this. Why? Because we have a explosion of the internet in the last decades. That means the internet of the 1992 was some network, inter-university network. Now we see the whole architecture of an internet. So it's how big or how was the how huge is the evolution of the network from the 92 till, okay, it's just 30 years. So application of the embedded system or Internet of Things, because I try even in my PhD work, what I do is I am abstracting everything to a single device. That means from my point of view, or from my thesis point of view, is that we have only one device that is spread out through the global, through the world. Okay, so that means everything in the world is part of a big device or a big system. And we have, let's say, application and smart system. That means we have some sensing, controlling, some functionality or some environment, and everything we can do through via an user interaction interface. And that means generally we can have access, okay, restricted access most probably, to any device in the world. Okay, as an application, is an automotive application. The modern car, nowadays car, has its internal internet, because it has, okay, from the information from 10 years ago, on a presentation from an automotive company, they say that, okay, nowadays means 10 years ago, a modern car has up to 40 microcontrollers inside. That means inside 10 years ago, a modern car has about 40 computers that was working together to drive, let's say, or to run the auto vehicle functionalities, all from the driving till the multimedia, air conditioning, and everything else. Okay, now let's see another example: environmental monitoring application. That means starting from just collecting data about the meteor, and finalizing with some smart agriculture, or some global, not global, but a smart air conditioning. That means, let's say we have a limited power and we cannot drive 2 or 3 apartments from the same device, but we can make some arbitration and switch between them in order to use a device with small power but to cover a bigger area. Okay, and so that means we have to make an let's say interaction between many devices. Okay, that means we have a big embedded system distributed through the internet, or we can say that it can be classified as Internet of Things. Of course, automotive application or Internet of Vehicle, even they can have. That means all the vehicles could interact between them, and not only between them, between environment and the and vehicles, vehicle to vehicle, vehicle to pedestrian, vehicle to the internet, vehicle to satellite. So it's another area of the embedded system growing. Intelligent agriculture, of course, and for our country, it is a big trend now, and there are a lot of, let's say, grants even on ag tech. That means they are waiting for a proposal how to introduce new technologies in the agriculture, because the position of our country is very good from the point of view of agriculture, but we still have problem to to make some value from that. Yeah, because let's say another countries that we have, they have a lot of sun, a lot of different bad condition, let's say environmental condition, but they are more efficient in agriculture than our country. In this case, we have to do something, and we can make something even some money. Why not? Okay. Industrial Internet of Things. From the point of view of industrial Internet of Things, we can connect devices, embedded devices. Yeah, because what is embedded? Embedded when we have some object or thing and we embed some microcontrollers in that. So we can embed microcontrollers in plant and robotic arm and environment, and we can make them to work together. Industrial Internet of Things, even in the production chain. Let's say the customer just click a button and is asking for some product, and surprisingly, but we don't have this product. In this case, it will make let's say an order to the whole in industrial Internet of Things, that it will involve manufacture, shipping, even some engineers to develop this product. And after some time, I don't know, depends on the complexity of the request, we will have it on our table. Yeah. So this means industrial Internet of Things, that everything is possible, and if that even doesn't exist, the industrial Internet of Things will create it or produce it and will give us. Okay, so just a remark that in the IoT as a system, we can see that the whole Internet of Things system can be abstracted as a single devices. What that means, that we have some information from outside, the system is processing it. Yeah, because system, what is a system? A system is a collection of components that are working together to produce a result. If you have by the way some definition what is a system, please write down in the chat, and we will check what you have meanwhile in another courses. And what I say, let's say like this, we'll make some comparison. So I'm waiting for some definition of a system. Okay, and in this case, when we are speaking about the embedded system and about the system, let's say, that is made on various components, the internet is also a system that is collecting information from the environment or from the area, processing it somehow and provide a result. Depends on the request where this result should be provided. Also it is, let's say, according to the system, from the structural point of view, it's made of different components. Those components can be part of only one device, or can be part of different device. But what we see here, let's say, is a system that is made on different device. More than it, this device can be abstracted, let's say, to the component interconnection like this. Yes, it's just a redrawing, and we imagine that we have a big PCB, motherboard, let's say, and we cut it in pieces, distribute it, spread out it through the internet, through the world, okay, in the world, and compensate the connection with some communication lines. And this is, let's say, my thesis in the PhD. More than it, okay, and from the structural point of view, it's a component, different components that are working together. From the functional point of view, it's a data flow of the information, let's say, or information flow that is going through the various transfer function, and and we have a complex function that can be split in some smaller function and distributed through the system. Okay, let's say part of the functionality is running on one device, okay, or on one component, and component can be on the same device or a different device, but the theory is like this. We have the system, we have different components or functions, and the components or function can be distributed through the internet. Okay, this is the theory of the Internet of Things, let's say like this. Okay, now an embedded system. If you have a single device or from the point of view of only one device or even on the whole system, we can have some group of components, okay? And by definition, let's say like this, an embedded system is a device or equipment that is made from on different domains, engineering, meaning mechanical engineering, electrical engineering, and software engineering. Okay, we have not or, we have and, because any device that we have, even this phone, is made on different okay, it has engineering on different domains. We have the shape and the button, camera, something like that. That means it some mechanical engineers was working hard to have mechanical functionalities. Okay, now we have some electronical engineering because we have some LED, some LCD here. So electrical engineering should work also to combine and to produce the electrical functionality. And of course, our slide of the on the monitor on display and the reaction is programmed by software engineers. That means embedded system is not only a mechanical piece or some electrical devices or some soft on the mobile phone. It's a combination of everything. And when we are speaking about embedded development, we should take in account all these three domains. That doesn't mean that one engineer should know everything. Yes, but it's a big team. Okay, there are some mechanical engineering engineers, some electrical engineers, and software engineers that are working together to make a product. So now, from the structural point of view, we will have a system is let's see here, yeah, a system is made it's consists on collection of components that are working together to provide a result. We can say that, okay, but we can not just say that a collection of components, but specific component, and we can have some component for sensing, actuating, communication, databases, user interaction, power management, some application components, let's say stopwatch, or let's say a calendar. Okay, in this case, it's just a software, it's an application component. It's a software component. Yeah. So in these cars, we will go through all the components, and we'll have a special approach in development for this component. Okay, so let's see. An embedded device has a, okay, from the point of view, we will have special components for user interaction. It's a specific component. It's specially designed for, let's say, for interaction with the user. Generally speaking, it is made from specific sensor and actuators that we'll see in the next two slides. What is a sensor, what is actuator? But it's sensing our actions and act back or give us a feedback via an action in order to establish a communication. So what kind of communication, or what kind of action, let's say, it can sense or act. Of course, we'll have different interfaces, like a binary interface, button or LED. That means it will sense the pressure, like button press, or a touch. It's okay. By the way, it's not okay. A touch to a touch button, let's say like this, not on the screen because it is another kind, but we can have binary interface that is detecting our action, binary action, yes or no. Another type of interface is one and two-dimensional grid interface. That means we can have keyboard. That means not only one button. We have 101 American keyboard. Yeah, in this case, this is organized on a grid, and we can detect. We have a matrix. We'll have it on the. By the way, in the next session, we will discuss about how to build a matrix of the case. Do not use too much 100 pins of the hardware. We can use only 20. Why? Because of some construction and software engineering. Okay, and same for the interfaces for the output interfaces. We can have matrix of pixels. It's a display. Okay, even our laptop display is not more than matrix of pixels. And okay, and three layers. We have RGB layers and matrix of pixels. Why not? And depending on how many light we give to a specific pixel or a specific color, we'll have some images, but it's just a bidimensional, two-dimensional grid of lighting. We can have, of course, different, not only lighting, by the way. Okay, of course, it's very important to have everything standard, because let's say in 80 and the previous century, every company started to build their own computer, and they face a problem that the mouse or some peripheral devices from one computer is not compatible with another computer. And I don't know exactly in which year, but appeared a standard IBM compatible. That means everything was standard according to standard, and peripheral from one devices can be switched and put on another devices. Same for the input-output interface. We can use standard input-output to redirect the user interaction interface. That means we can have information from the keyboard or via a remote keyboard, via a socket from the internet, but we will use the standard input-output interface. And you know about that, it's scanf printf function. And scanf printf function, printf can be directed to the display or to an LCD or even to the internet or even to play a Morse code on how to say, speaker. Yeah, why not? Just printf hello, and it will play. If in case of the display we have a char on our display, okay, and in case of Morse, every char will have a sound or music, let's say, like this. Okay, and another complex interaction interface, that means we have a touch screen, we have an LCD, we have VR. By the way, you are invited on our workshops. We'll have how to build on VR, construction mechanical, by the way. It's also engineering. And another, let's say, interfaces with voice recognition and speaking. This is another complex, but we have simplest, the binary interface, one or two display and the keyboard, standard input output that can direct text information, let's say user information from one from any to any devices or from any devices, and another more complex interfaces. Okay, operating system. Of course, when we are speaking about system embedded system, we should manage something. And from the software point of view, we have few resources or system resources to manage. That means we have to manage peripherals, yeah, we have to manage processing time, and we have to manage memory. This is the three main resources that should be managed on the application. So in this case, we need some operating system, and the simplest operation system, even it's songs very simple. Yeah, we have we have operating in the infinite loop. Even an infinite loop should be qualified as an operating system. Why? Because in this infinite loop we are managing everything. Yes, it's simple, but everything we have to program in details. Yeah, but we can have also a sequential system. We can have, that means non-preemptive system, and preemptive operating system that allow to run on the same device many tasks in parallel without synchronizing even. Okay, and every task doesn't care about existence of the another any parallel process, let's say. And we'll have an example, let's say real-time operating system FreeRTOS. If you would like to know what kind of operating system we can run on a microcontroller, so FreeRTOS is one of the most popular in the embedded system and do-it-yourself systems, yeah, or open systems. Because in automotive, let's say, we will not use a FreeRTOS. We will use, let's say, something more specific, more qualified, safety qualified, and automotive qualified. Let's say in the medical devices, of course, we'll have another requirements. But for general purpose, let's say even home appliances, we can use FreeRTOS for sure. And even I recommend to use FreeRTOS. Why? Because the management of the system is transferred, the responsibility of the file is transferred to the people that are managing to provide the operating system. Okay. Sensor. So we'll have a special class for sensors. And what a sensor is? A sensor is a device that is converting the external physical environment parameter into information, going through the mechanical part, electrical side, and the software engineering part. In software engineering, such components or the resources we will name drivers or software drivers for everything. That means software driver should take in account everything or from the electronic device in order to manage it. So what is a driver? A driver is specific library that is working with the hardware. Okay, if we have a library that is working with hardware, we can say that this is a hardware driver. We will discuss in this course about sensor classification, acquisition signal, signal conditioning, and signal processing. We will discuss this on the specific section, one of the next. But now, diagnosis. What is diagnosis? Okay, we are acquiring information, but we have to detect if this signal is a valid signal, first of all, if the device is providing correct information about the environment, or that means you will have, let's say, 100 degree of Celsius, or Celsius degree. What that means? One situation is that sensor is broken, another is too hot, and we don't have to touch it. Okay, and in this case we have a specific method. Just by measuring the sensor we can detect what's happening. Okay, and we detect the symptoms of the from the signal. Also, we will have diagnosis qualification. If we have just some noises and we don't have to react to some noises, and to open the door if we have too hot, because it was just few microseconds of the hot situation. We can ignore it. Okay, in this case, we have some qualification to qualify this situation or this symptom, or to not qualify, just ignore. And of course, we can manage errors. We can generate errors from the diagnosis qualification, from this generated by the symptom detection. Okay. Next, we have actuators. This is the inverse function of the sensing. Sensing meaning to transform the physical parameter, physical parameter of the environment into information. Actuators are doing vice versa. Is transforming information. I want, let's say, hot or I want to, how to say, to dry or to cool something. Okay, in this case, we have this information. I want, let's say, 20 degrees. In this case, actuator will have to act to the physical environment in order to achieve the what we need. That means we transform information into the changes or into actions to the physical environment. We don't change, let's say, not override the physical environment parameter, because we cannot do that. Because in case of sensing, we can measure very exactly what is the temperature. But when I want to change this temperature, I cannot do that for the whole room. I can make some actions in order to change the environment. So here we have not changing, but generate actions according to the internal informations. So we'll have also actuator classification, the actuator methods. We'll see what kind of methods we have. Also, we'll have to condition some signal, because we'll have some fast changes inside. That doesn't mean that we have to change it outside very fast, because most probably we'll see next section about the protection. The motor will not be able, let's say, to be configured to change fast the signal from the 0 to the maximum. Most probably it will break even the device. In this case, we have to condition the signal that we are applying to the actuator. Of course, we have information, but information is software. It's just some states and most probably requests. But when we have to provide an action, we have to convert it into the power. And power is not from the information. In software, we don't have physical power. The physical power we can get from the power source or power supply, and information from the application just control this power supply in order to have the specific action. That means we'll go through the power converter. Protection, let's say, are mechanisms that are limiting the functionality depending on the certain symptoms. Let's say that the engine, yes, or the DC motor is very hot. It's very hot, and if it will continue to drive it on the full speed, it will damage, or will damage itself, or will damage something, or something will happen. In this case, what we can do? First of all, we can have some notification to the user at a certain level, or after that, we can limit it to the high speed, to not have higher than this. But if you have higher temperature, we can even derating. And most probably you already seen such effects when the system is overloaded, the motors are driving lower. Let's say the battery is not enough. In this case, we cannot have a kick down on an electrical car. Or even we can lock, let's say, okay, I have not enough battery. So in this case, I will provide information. I'll provide power only to the dashboard from some LEDs, but sorry, I don't have enough power for driving the car, the wheels, let's say like this. In this case, that means we'll implement some protection. Okay, some special functionality. Control. What is a control? Okay, when you say that, okay, I'm controlling something, what that means? It's abstraction that defines functionality of the system in order to solve some specific problem. So we'll have some, we will analyze some methods, even we'll implement, okay, vending machine, sorry, finite state machine, not vending machine, okay. Open loop control, on-off control, PID control, this is proper, okay, on-off control is just on-off. PID, that means proportional, that means we want some fine tuning control of the system, control with state machine, finite state machine, sorry, remark, yeah? Or control with, that means when we are controlling, we are in the first state, after that we are going to the next state, and we have some behavior, we are going after that another state, and we have a machine, let's say vending machine. When we are putting some money into vending machine, that means you'll see, even you'll feel the changing on the state. First of all, I'm the state of acquiring the money. After that, we are checking the money. After that, we are providing an information. Please check the product. Waiting for the selection. Yeah. After that, when it's selected, provide, open the door, close the door, and go to idle state. This is control with finite state machine. Control with programming interpretation. That means we can have a interpreter inside of our application where we can place just some commands. Let's say a good example is CNC machine, 3D printing, yeah, and there you are placing some G code stream, and it is interpreted as program to build you a mechanical part. Yeah, that means we have some control with interpretation of the program. Fuzzy control. Most probably you already heard about the fuzzy control or wash machine, Bosch, or depends on what you have at home. Yeah, and it first try to from via a fuzzy means bug. Okay, I'll not translate now. A fuzzy mechanism is detecting what will be the best control parameters in order to wash you to have a perfect washing. Okay. Wash, well, laundering. Okay, communication. It's, for me, from my point of view, communication is just interfaces. As I told from my thesis, that is just communication wires, but depends on the environment through what we are passing this information. We should ensure that information is going from the point A to point B. Let's say when I'm speaking with you, I can speak you in the class, and you will have direct access to the information on the voice. But now when we are online, we are using all the technology, in order for my voice to go to your ears. Yeah, that means, let's say we have the whole communication chain. Everything you know about the communication we have here. We have network, okay, the internet. We have physical protocol. That means I have some cables or wireless. Okay, we have some logical protocol. We have TCP/IP. We have some communication between components. That means my PC have components, have some wires or some okay, some wiring PCB. There we have another kind of communication. We have communication between devices because my PC is made on different devices. Let's say microphone as a device. After that, microcontroller and so on. Depends. And finally, we have here internet, yeah, and cloud communication, most probably because my what I'm speaking is involved, okay, the system that is providing this webinar has a cloud system that is connecting me with you everywhere, from everywhere. So means, from my point of view, communication is just a communication chain and can be replaced with a single line. Even as I told, I can even not have some technology, but now I need technology in the hardware, on the let's say engineering systems. We need some electronics, some mechanics. That means, in this case, in order to transfer information, we will need some engineering, mechanical engineering, software engineering, and electrical engineering, in order to ensure that information is going from one point to another. Let's say you have a state in your device, let's say mobile phone, and you want this state to mirror on another device. Imagine what you will need for that, and for sure you will need everything from here. Okay, from the point of view of programmer, is just open a socket and send a data. Yes, but it is implementing everything from here, and we will go through and we'll see how it can be done. Okay, next, cybersecurity. What is cybersecurity? And I will go few steps back. And when we are speaking about diagnosis, we are speaking about safety, because I'm monitoring, and after that I have some protection. In this case, I have some safety mechanism to protect humans against the injury from the device. But in the case of cybersecurity, I protect device from the human harm to the system. In this case, cybersecurity is protecting everything. It should protect access. It should protect the storage. It should protect even keypad, yeah, from the access. Not keypad, user interaction, because when I'm introducing a password, okay, I should even make some checking of the password to stop introducing how to say many times. Let's say you have only 3 attempts. Okay, of course we have some operating attempt, operating safety, because security, sorry, because I can let's say I can have situations that I was too smart and say that, okay, if something happening in the room, I should release the lock of the door. So what I can do, I can hack a sensor and the door will open without any password. In this case, I should think about what I can do in order to ensure the security. That means to protect the system against the human unauthorized access. Okay, now I will go through the attendance. So please, let's register it. So be ready to enter in the attendance. We have here course attendance. you have only 1 minute for this. You have two groups, but the key is the same. Yeah, and the key that it will be open not more than even less than 1 minute. Okay, so please go in and register. So please confirm me that you succeed. By the way, you can somebody. Oh, but you got the key to register, no? Did you receive the key for registration? Just a second. Okay, just a second. I will give you the key. I will. Okay, just I will. Okay. So please register now in a few seconds. It's just one click. Please confirm that anybody from the 181 is registered. Anybody, just say yes, I'm registered from 181 and from, okay, just type the number 181 and please say that anybody from the 182 is registered to check if yes. Okay, you have the key. Please, you have not more than 30 seconds, let's say, in order to continue, because we have another part of the so that's all. YAOQFK. Go further. Architecture. So go to the second, because now we just had a short of an overview. What is an embedded system? What are the part of embedded system? Yes, we already pointed to the some architectural concepts, but let's go through the architectural things. Okay, architecture refers to the some fundamental structure. Most probably you already have some courses on the software architecture. Please just confirm me yes or no. Did you have any courses related to the architecture? Yes, no? Software architecture. Okay, but even if the answer is no, architecture, we can understand it very simple. Imagine that the architecture, let's go to another domain in the construction. And now you most probably heard about the architect that are designing the architecture of the city. That means when we are designing an architecture of a city, that means we are designing an architecture, system architecture, yes, or a domain architecture. This we can compare with an architecture of a car, yes, and from the point of view of engineering. And in this case, an architecture what is doing is planning everything in this by drawing where is the room, where is let's say from the city architecture, we have buildings. From the point of view of building architecture, we have building with some levels and some rooms. Yeah. Okay. We have computer architecture, but you was involved in okay. We learned the computer architecture itself, not the architecture, not the software architecture as a curricula. Okay. Okay, we will solve after with the K. Most probably you are not on the, okay, we'll see. Now, let's go to the next slide, because this, what you see here, we are speaking for, this is some means from the wiki. As I told, wiki is not the official, but we can see what people are thinking about. Yeah. So going through from the software architecture to the house architecture, we can see some similarities, because okay, it's about the architectural approach. And when we have a building, or let's say this is a house, yes, we can see the rooms here. We can see here where are the windows. That means we have the general architecture. After that, we have some design. We have the lighting, we have the switching, we have everything, and we have a system architect. After that, we have let's say electrical engineering here. We have some mechanical engineering that say that okay, the walls will be made on some material and so on. And this is completely similar to the building architecture. Okay. And now when we are going to the process, we'll see in the V model where is the architecture in the V model development process. I don't know what kind of process you will use in the company when we are or in the engineering, what we will do in the next few years. But according to the V model, we have some layers, and we have this Y. We have a branch for development and a branch for validation. And first of all, we have here a client, let's say somewhere here, and it's asked for a device with some requirements. Those requirements are converted to some specification. The architecture or system architecture is getting the specification, what should be done, and build the architecture or make a architectural design. Architectural design that is, let's say, distribute the functionality, it define the components, okay, and distribute the functionalities through the system. That means it's more, architecture is more related to the structure, detailed design. And after we have, let's say in the software, let's say like this, because it's more related to you, we have software architecture that just define what the components and interfaces. That's all that it's doing, and just say this component will have the next functionality. After that, we have a software designer. A software designer has what? The functionality and requirements, functional requirements, has interfaces and provide a method, but not the code. It is designing using the universal modeling language, because the function itself, 2 + 2, let's say like this, it's not related to the programming language. It's related to the function that should be done. Or let's say a function braking for that means how should be done the braking system. It's not related to the programming language, or most probably it's not related so much to the what electrical components will be used. It's just some diagrams, okay? And we are going after to the coding. Now everybody, okay, it's hype to say I'm a developer. For me, if you're thinking about, but the developer most probably what you know is it's combining you think about, okay, it's architecture plus designer plus coder. But for me, developer developing or implementing how to say it's the lowest stage that should be done. That means you don't have to write even a line of code before to know what to do. Why? Because coding is just a translation of the design into the code machine, right? Code machine, okay, into programming language. So in case of going through the code, after that trying to provide to the client the architecture, you'll have a big problem, because every engineer like its own code. It's say that, okay, it's the best code you can ever find in the world. Yes, but it's hard to convert it back to explain to the client, because clients say, I give money to this, that you are the best. It's your problem, it's your feature, you are the best, but I need not you and your stars, okay? I need my product that you have to do, and in this case, please provide me what I need. And to do that, in order to do that, we have the validation. And when we are writing code, we have detailed design, we have some interfaces and some programs or functionality flows that we are checking with unit testing. What we are checking on unit testing, if we have the right interfaces and if we have some flow in the program, not what code we are using. Architectural design, when we are combining components, we match the interfaces and we see that everything is working together. We have integration testing. After that, we have system testing, that we have some scenario that we say, okay, I open the door, switch the light on, close the door, everything is well. Yes, everything is well. That means we are validating the some specification from the requirements. And acceptance testing, that means client is coming here and we make a demo, and he's trying if the system is working, performing well. Okay, but acceptance testing most probably can have some test, non-functional test, like how you did develop. Did you use an architect? Did you use a design? Okay, and here it's not only functional test, we have more. Okay, next, system. So we can say that system, from the architectural point of view, a system is a collection of components that are working together to provide an result. So we have information that is entering to the system and it is reporting. Okay, we don't have systems without output, because it's just a black hole, just collecting information without providing. Even a hard disk, okay, or SD card is also an output, input-output system, because first of all, it's registering information. After that, it's possible to take it out. That means we cannot have system without output. Same as we cannot have systems without input. Okay, we have, but this can be qualified as some random generator, let's say, like this, or generation information. Or we have an SD card that it's built to provide some information as it is. So in case of the system, we can have a system with outputs, but not only with the input. But generally speaking, any system has input and has output interface, and it can be split, the functionality can be split in different components in order to achieve and to simplify the engineering work. Same for functionalities. Okay. Now, if we'll go through the hardware architecture and the embedding level, okay, I have here an approach from bottom up, and we'll have first, but maybe top down will be better for you, for novices, but most probably you already know what is the central processing unit, CPU. That is make some programming. We have peripherals at the next level, but let's go through. Let's see what is a processor. And the processor is made on two parts, by the way, a control part or control automat, control state machine that is providing execution of the program that is in the program memory. Yeah, it's the program counter. It's selecting the instruction and providing it to command decoder. Command decoder is configuring everything. Yeah, and if this command is a control command like if, else, for, while, let's say like this, abstracting, or jumping, or calling a function, or returning from a function, or an interruption, that is a command for the control state machine. We have another state machine, execution state machine. This is executing depending of the this means we have adding, subtracting, arithmetical, logical instructions. And we have the third is transfer instruction that is not related to any state machine. Is related just to transfer information, just configuring the data flow through the. So we have three kind of instruction: controlling file instruction, arithmetical, logical instruction, and transfer instruction. Okay, and the MCU, let's say microcontroller unit, is made on a on CPU and IO. That means microcontroller unit or microcomputer, we can say, because if we will speak about computer, we have processor, even your laptop, and we have some peripheral, let's say USB, keyboard, and so on. In this case, a microcontroller also can be qualified as a microcomputer because it has a CPU and various type of peripheral. Going through, we have microcontroller now. Next level, system on a chip. Okay, but let's say here, what is a system on a chip? System on chip is a kind of, if a microcontroller is an CPU that has embedded inside some peripheral models, generic, and system on chip is a microcontroller that already has some IO, yes, but it is also has other specific controllers, and the very good example of such device is the phone. Okay, if you open it, you'll see that you have a PCB and only one big chip. That means comparing to the phone that was made 20 years ago, we can see that we have microcontroller separately, USB controller separately, keyboard controller separately, everything separately. Now, in order to have less expensive device or process, everything was integrated and was done in the single process on the manufacturer side. And that means, let's say like this, we have an audio system that we have here, processor, we have some peripheral devices, yes, for the line, and we have USB controller also is embedded in. So we can say, by the way, if we are speaking about the Raspberry Pi, it is also using a system on chip. Okay, all the computer is on this chip that you can see on the Raspberry Pi, except the memory okay, because we need some memory, and as I know, is the wireless controller, but the video display controller and the keyboard controller, okay, USB controller, audio controller, and everything else is put inside on the Broadcom chip. That means when we are speaking about Raspberry, we don't have there a processor, powerful processor. We have a very complex system on chip, or all-in-one a pocket PC. Yeah, in this case, I will have an example, let's say, of this chip that we can use to have a player. We are going deeper inside, or vice versa. We are going. We have here electronic control unit. What that means? We have a electronic control unit. We have some micro controllers or some system on chip and other different chips on PCB. Yeah, according to the, and we have a system on chip or microcontroller and some components that cannot be, because system on chip can be developed or manufactured for a specific, when we have mass production. Let's say we have a mass production of the phone, then I have chip, system on chip for the phones. But if I would like to make some specific, I cannot build a system on chip. I'll get a microcontroller or a system on chip for specific problem and will combine with different component. I'll have an electronic component unit. This is the difference between system on chip and electronic component unit and microcontroller. Okay, and when we are going outside, okay, we'll have something like this. We have the embedded device that has also mechanical parts, not only electrical. Yeah, and we have the shape, and we'll have also even this radiator. It has its own function. So let's go through the system architecture. Every component, this is a, let's say, leveling of the embedding, but every component from here that we discussed about can be made by layering. Okay, can be split on layering on the hardware part. Yeah, hardware is everything you can touch, or it has some weight, and software is something that doesn't have weight or doesn't have shape. It's about the software programming. So mechanical engineering and the electrical engineering is related to the hardware, and everything else, okay, is software. In this case, when we are developing those components, we will have some layers, some abstraction, because right organization of the software will provide us with more flexibility. That means for the microcontroller, we can have a driver for the microcontroller, MCU abstraction layer. And in our case, we have Arduino.H. This is an abstraction or on hardware abstraction layer. Yeah. After we have some components from the eBay, let's say on ECU. Yeah. In this case, we'll have a driver for the ECU. Let's say driver for the module from the eBay that I bought. Let's say microphone or driver, stepper driver, servo driver, or doesn't matter. Service is related to what a device can do. That means if you have a robot, go forward. I have a service, go forward, and we'll have 2 wheels on the ECU, 2 motors on the ECU, and it will start both together in order to provide the service going forward. So the application after that is using those servers. Layering, organizing in layers will make us more flexible. Now, depending of the application, but all the components from here can be developed using this concept, and we'll have function like get, scan, receive, and vice versa. We'll have set, print, while, and send. Okay, now a good example is AUTOSAR open system architecture that is providing a kind of Windows for microcontrollers and automotive. That means it's allowing to connect everything from everything, making a virtual functional bus and at the level of the and the application level. And that means it will use any components or on any devices through the gateway or through the vehicle bus, vehicle internet. Okay, why to use that? Let's say like this. They and now AUTOSAR automotive open system architecture providing stacks for the system, for the memory, for the crypto, for the wireless communication, for the communication or abstraction, and everything is not. It's just complex driver, but it's providing some components under runtime environment. And the application will just say open the door, close the door, get the temperature, and so on. And why to use such experience? Because a lot of people was working and decided, okay, this architectural approach is good, and we see how big is the community of the AUTOSAR. Now, as we discussed, a system is a collection of the components that are working together, and I have some examples that I built on my own. Okay, I have the system architecture with the functionality and the layered architecture where I have, let's say, here I have microcontrollers and Arduino Edge that is using digital read, digital write, analog write, analog read, analog write, and you are using some microcontroller pins. Okay, I have here some Arduino components, and here I have some drivers for Arduino components, and on the upper layer I have some services. And in this case I just get the temperature. Okay, temperature I can get from one sensor or another sensor, because I see I have some different functions. Okay, another example is ARM control. I have some sensors, I have some actuators. Also, I have here Arduino. Yeah, here we have Arduino. Here I have Arduino.h. Here I have eBay models, and here we have drivers for eBay models. Here I have the application layer for communication or servers, and on the robotic arm application I can say go to X, Y, Y coordinates, and it will do automatically. Functional, we can say that, okay, we have sensing, collecting information, we have some stages or functionality that is providing data flow to the application and back to the action. Yeah. From the operating system, we have robot operating system that is not related to the operating system, but how to interconnect models in device. So we have nodes. That means some components that is providing some information. If somebody is interested, please, as a reference. So finally, the embedded system, okay, is a device that is made on various domains like mechanical engineering, electrical engineering, and software engineering. And in these cars, we'll have seven generic problem to solve, and in this case you will be able to define any application you want. Even you can use those laboratory works to your Internet of Things PBL project. The report will have the next format. We'll have title, statement of the problem, objectives, last 3, introduction, materials and methods, results, discussing what can be optimized, conclusions, and the schematics, by the way, and source code are the annexes. Here in results, you have to provide some diagrams, concepts, follow chart, sequential diagram, maybe architectural approach that we have, something like this I want to see there. Yeah. Okay. That's all. If any question, please ask me. regarding the, we can try now to solve them, but let's say first of all, please some questions on the course. Please, anything? Why Arduino? I'm using the Arduino because but what is Arduino? Arduino is not a microcontroller. Arduino is, when we are speaking about the Arduino, it's like we are speaking about Unix, okay? Because Arduino is just a standard or is a open hardware community that is providing just some architectural approach. But if you see the microcontroller, you will see that there is an AVR microcontroller or STM microcontroller or ESP microcontroller. Arduino is just that we are using open hardware approach. So why Arduino IDE? I don't like Arduino IDE, but this is a kind of it's a kind of very quick, we can try to make some simple application. Personally, I'm using more complex IDE like Platform IO or Slowbear from the Eclipse. I'm not using for my project Arduino IDE. I'm writing programs not necessarily using Arduino library. Arduino library is a kind of standard library that you can find even in Linux, let's say like this, because when we are speaking about the Unix, we are speaking about the concept, okay, not about the Unix, let's say about the Linux, yeah? When we are speaking about the Linux, we are speaking about the open source community. When we are speaking about the Arduino, we are speaking about open hardware community. So in this open hardware community, we have a lot of libraries that we can use or can not use. Yes, when I say that we are using Arduino.h, I'm referring that you can use the abstraction. You can write your own, you can have it from an microcontroller provider, MCAL layer. Usually an STM is different, but Arduino open source, open hardware, it's generalizing everything. And if you will use a board Arduino compatible, it's like Arduino compatible is like IBM compatible. If you'll use an Arduino compatible board, that means all the functionality from the Arduino will work. It's just for simplicity. Okay, if you want to use more deeper, to go deeper inside to understand how the microcontroller is working, then yes, but it's another in this course we don't have to use any programming language, we don't have to use learn any computer architecture materials. We want to make some embedded system. For reference, we will use open hardware concept. Did I answer? Anything else? Okay, then